Okay, my name is Jeong Ah Kim from Catholic University. Today, I'm pleased to present our research on lightweight and robust pumping recognition for smartphone-based identification. This work aimed to make a vein recognition technology more accessible and practical, particularly in mobile and healthcare environment. Following agenda, as- uh, I will talk with the following agenda. Our research begins with a practical question. How can we implement highly accurate biometric identification using just a smartphone and a very compact camera? So we focused on palm vein vacation recognition because of a high security and contactless nature. This study developed a deep learning-based system optimized for mobile edge environment. So we designed a custom near-infrared camera module comparable with the smartphone and built in a CNN-based learning model capable for performing reliable real-time environment. In healthcare environment, patient misidentification remains a major issue because barcode bands can be damaged or lost. And verifying identification is difficult in unconscious or nonverbal patient. But palm vein recognition addresses this by offering non-invasive, highly accurate identification. Vein projector already assisted with um, vascular access in pediatric patient. Our system extends this capability by integrating identification and the detection into a single mobile accessible solution. These slides outline our full system architecture. We begin by capturing vein imaging through a near-infrared compact camera connected with the smartphone or PDA. This captured image um, undergoes pre-processing, including contrast enhancement and normalization. This data is passed through a convolutional neural network CNN architecture with the extract of vein-specific feature and classification. The final stage is comparison with a secure template database uh, for identification and verification. Each component was designed to operate within a limited memory and computational power of a mobile device. I think that our contribution integrated to critical technology. First is minimize the near infrared vein detection camera comparable with the smartphone. This resolved the hardware variables in a traditional system. The traditional system, the cost of the traditional system is so high that every hospital has an obstacle to adapt to that technology. Secondly, we develop ensemble CNN architecture that significantly boost recognition accuracy. By training the model on both correct and incorrect samples, the model learns to distinguish fine-grained features more effectively. This diagram illustrated entire training and deployment pipeline. We begin with the dataset collection and pre-processing, followed by training a high-performance server using VisionNet as our basis CNN architecture. After achieving the stable performance, we applied the model compression model compression techniques like quantization to reduce model size and latency. This compressed model was then embedded into a mobile application using a TensorFlow Lite. This process ensured that model remains accurate and fast enough to run directly an Android smartphone. Our training data comes from two sources. First one is KCTRS multispectral print data set. This data set contains 7,200 grayscale palm images across the six different wavelengths. To improve real-world application, we also collected 3,000 supplementary images under hospital-like lighting. The resolution was set to 640 by 480 to balance the accuracy with the mobile memory constraint. Each user provides 20 images under slightly various conditions, enabling the model to learn intra-user variability. These efforts were critical in training a model that performs reliable in uncontrolled environment like a hospital. To enhance the robustness of a model, we applied several image augmentation techniques. These included change in image angle, brightness, adjustment, and blurring. By training on both the original and augmented version of each image, the model was uh, able to generalize better than the unseen conditions. This process helped the system maintain high recognition accuracy, even in non-ideal environments, such as emergency rooms or poorly lit corridors. As I mentioned earlier, we used efficiency net as the base convolutional neural network CNN architecture due to this architecture has high is a high accuracy and computational efficiency. Efficiency net scale network depth, width, and resolution in a balanced way, making it ideal for mobile environment. We also developed ensemble architecture where parallel convolutional um, paths were trained both on correct and incorrect samples. This approach enables the model to fine-tune its feature extraction capability by adjusting weight parameter across the path. The architecture consists of five convolutional layer with an increasing filter size. And our architecture was trained over 50 epoch using Adam optimizer. Uh, this resulted in an initial classification accuracy of 98.6%. After training, the model was embedded into a mobile application using an application built using a Flutter and Dart. The app supported two main functions: registration of a user's palm vein and real-time identification. To ensure the modularity and the portability, the app was built using a MVC architecture. Each submodule was designed to replaceable depends on a platform and the device constraint. This structure makes the solution scalable to other mobile operating environment as well. To enable efficient inference in a mobile environment, uh, because the mobile environment has limited computational resources, so we applied the quantization and the model compression techniques. This is especially important for a real-time application like a mobile identification, where the responsiveness is critical. We evaluate our model's performance both quantitatively and qualitatively. The dataset was divided into training and validation and test set. Final trained model achieved an average classification accuracy 99.5% on test data. The average inference time is between 120 and 200 milliseconds, confirming the system's suitable for real-time use. This is a demonstration. Okay, to summarize, this study proposed a smartphone comparable palm vein recognition system using a compact NAR camera and the scene-based deep learning model. And this system achieved 99.5% accuracy, and significantly improving the baseline CNN result and performing well in real-world environment. I think the key contribution includes your past CNN architecture defines the weight parameter using both correct and incorrect sample. Moving forward, several enhancements uh, will be our planned. First, we aim to reduce the power consumption and optimize the hardware integration to improve the mobile energy efficiency. Second, we will developed cross-platform versions, including the iOS, and explored the multi-device synchronization. Third, to ensure data privacy, we plan to implement on-device encryption and private preserving protocol. Finally, we will conduct a pilot deployment in a hospital environment to gather feedback and adapt the system to real operational demand. Through these steps, we hope to contribute safer and smarter biometric authentication across multiple industries. Thank you for listening. This is the end of my talk. Thank you.